Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on the 27th of June, 2025 T, 17 hours, 59 minutes, and 1 second .0000. This paper, published just a few days ago, introduces a framework for video editing that ranked first in user studies for quality and consistency. The paper is titled Shape for Motion, Precise and Consistent Video Editing with 3D Proxy, and as we'll see later, the visual results are really impressive. It tackles the problem of making precise, consistent edits to videos. The core idea is to create a 3D model of an object, edit that model, and then automatically apply the changes back to the video. Also, the authors shared the official GitHub repository for this project. Now, the full implementation isn't public just yet, but the page is up with a note that the code will be released soon. So it's definitely the place to watch if you're keen to get your hands on it. Alright, so let's dive into the first figure, which really showcases what this Shape for Motion framework can do. We see a few great examples here. The system first reconstructs a 3D model from the video. It uses a technique called 3D Gaussian Splatting, which is a method for representing a 3D scene using many tiny, colored, semi-transparent blobs. Once they have this 3D proxy, they can make precise edits, like rotating a unicorn's head or adding a tree to a car. Then they render it back. The final videos, as you can see, maintain these edits consistently throughout the motion. Okay, so this figure really breaks down that process into 3 key steps. First, from the input video, it reconstructs a consistent 3D proxy. This involves creating a canonical mesh, which is like a standard neutral 3D model of the object, and a deformation field, which tells that model how to move over time. Next, you just edit that single canonical mesh, and the change is automatically applied to all the frames. Finally, it renders the edited geometry and texture, using them as control signals for a generative model to create the final, consistent video. Building on that idea of editing a single mesh, this next figure gives us a closer look at how those edits are propagated so consistently. It's what the authors call a dual propagation strategy. So on the left, you see that canonical mesh, the neutral 3D model. A user makes an edit to this one single mesh, like changing the character's pose. Now, the change is propagated along 2 separate paths to ensure consistency. The blue arrows show geometry propagation, which transfers the new shape. The orange arrows show texture propagation, which maps the original color and details onto that new shape. This dual approach is key to creating a final, consistent mesh for every frame. So once those geometry and texture edits are propagated, the final step is rendering the video. This diagram shows how they train the generative model for this. It's a 2-stage process called self-supervised mixed training. In stage 1, they train a geometry controller, which learns to follow the shape of the edited 3D model. Then, in stage 2, they freeze that controller and train a separate texture enhancer. This part focuses on adding the correct colors and fine details, ensuring the final video looks both realistic and consistent with the edit. Alright, and this brings us to the visual results, the side-by-side bake-off. This figure compares their model against 4 other leading video editing methods. On the left, the task is to rotate a dog's back half by 30 degrees. On the right, it's to change an SUV's sleek roof to a taller, boxy design. You can see their results are incredibly clean and consistent across the frames. The other methods, however, really struggle. They either create strange visual artifacts, barely make the requested change, or, in the case of tune a video, completely distort the video. This comparison really highlights the power of using that 3D proxy. So to wrap things up, the key innovation here is moving video editing into 3D. By creating a consistent 3D model of the object, the Shape for Motion framework allows for edits that are far more precise and stable over time than what 2D methods can achieve. The results, both in direct comparisons and on quantitative benchmarks, like the CLAP score, which measures how well the video's content matches the edit's intent, really bear this out. While it still has challenges with fine details like shadows, it's a huge step forward. That's all for this week's AI Research Roundup. Thanks for listening.